two squares is sort of our little diagrammatic paradigm for the rest of today. That every time we're going to try to span or work with two squares worth of space that's in the floor plan. And it doesn't matter what the function is, whether it's ecclesiastical or secular or residential or commercial or industrial. The idea is we're going to try to span the space, which is 2 bays long by 1 bay wide.
Today our drawing is of two squares. We will have the distance of two squares within our floor plan. We will have the distance of two squares of space within our floor plan regardless of what type of building it is. We're going to enlarge the volume of space between the two squares.
So the first couple of images here shown on the left that are taken from the text here, some of those small little thumbnail images, refer to a bearing wall. And the notion of bearing wall is that, and we'll do these in an axonometric projection, where we'll simply go off on a diagonal to the same distance 4 times. And then complete the height of the space.
The two small pictures on the left are from the text. The pictures are of the main structural walls. Without the main structural wall, the buildings would be unable to stand. The drawings of the main structural wall is drawn off the points of the 4 points of the square diagonally. Then you connect the 4 straight lines are drawn. Then you draw one straight line at the top of the box.
And the bearing wall is a massive mural entity made of component parts. So these bricks, there may be a reinforced concrete base system that actually structures this space, but potentially if this brick wall over here was actually feet thick, made of solid brick or a type of stone, it could be referred to as a bearing wall supporting the loads that are carried across here. But I suspect in this building in the 1960s that there's a grid work of reinforced concrete columns, and this is just sort of a decorative infill for the wall. So it is a brick wall, but it's probably not a load-bearing wall. When actually the wall itself is carrying the load of the building, it's referred to as a bearing wall, and that's a real simple type of historically deep type of structural system, where then it allows for elements to be punched out within its thickness to allow for lighting or entry systems into that.
On the structural wall, there's a large separate artistic accessory. This separate artistic accessory may be reinforced with concrete within the enlarged volume of space between the main structural walls. This artistic accessory could be considered a main structure wall if the brick or stone used is 12 inches thick. But I think in the 1960s building layout, and this separate brick wall is likely just decorative. The wall that the decorative brick is added to is the main structure of the support wall. Within the wall, the windows and doors may be added.
So an extraordinary example of this is in downtown Chicago in the second image here, where at one point, for a very fragile time in history, it was the world's tallest structure at 17 stories, and it was all bearing walls. It's called the Monadnock Tower down on Dearborn, in the south part of the Loop, and because of its intense weight, if you were to build, let's say, for instance, a typical wall section out of brick, maybe 14 inches thick, and you were to rise from the street level up 17 stories, the weight of the brick would be so sensational at the top that it'd be too much capability of faltering or buckling on that load. So in fact, what happens at the Monadnock is there is a pyramid created along that wall such that the top element of brick is the 14 inches, and the bottom base of the wall at street level is 6 feet thick. So a very elegant pyramidal effect of masonry was created to be the major outside walls of the box of the Monadnock. And the presence of that is still felt today because obviously the structure hasn't changed since the 1880s when it was built. So when you walk into the Monadnock from the street, you pass by 6 feet of brick. It's like you're walking into a cave to get to the first floor retail.
An example of this is in the second picture, the Monadnock Tower on Dearborn on the south side by the Loop. At one time it was the tallest building at 17 stories high. It is made of all brick and all the walls are main structure walls. The Monadnock building is brick and 17 stories high and 14 inches thick. So the problem with this is that the combined height and weight of this building would normally cause it to collapse. To avoid the building's destruction, a pyramid is added to the main structure outside to balance the weight. The pyramids are beautiful added stonework on the outside walls. Today, the Monadnock Tower is still the same as it was when it was built. When you walk in, you pass through 6 feet of brick, kind of like a cave, just to go shopping.
The second typology we accomplished in the first sketch today of the 2 columns in terms of post and lintel, columns and beams. And that will take again the corner posts with a beam that runs between them. To achieve the same height as our bearing wall space did. So the goal here is to keep the size of the space the same, but to convert the different types of structural entities that house that space. But in the classical tradition, if this was a stone structure, you should be able to see that in terms of what we drew initially on your first sketch and how close those columns were together, that was due to the fact that stone can't span. We'll get to that in the second half, the physics half, the properties of materials. Stone can't span a great distance. So in order to make this first span work, they would have had to go in and put secondary columnar elements in there to create that span. And that would run all along sides of it, and to complete the temple type here, it's entablature wood raised above it. And eventually it's a pyramid roof.
The next type, using the square shape of 2 columns, the vertical support structure of a building, is the post. The lintel columns and beams are the horizontal support structures of a building. We will take the corner vertical post with horizontal beams that run between the posts to make the structure the same height as the previous main structure wall. Therefore, it has the same goal of achieving height and sturdiness, but it looks different. Historically, if stone structures were used for the post, the up and down stone structure, and the stone was used for the lintel columns, the side-to-side stone structure, if it was made with a stone in a square shape, it could not bridge a large distance. Therefore, to make this work, they added the secondary columns to create a bridge-like effect on all sides of it. They completed this with the temple type 3-sided and eventually became a pyramid-shaped roof.
Now, because they need to have that usable space on the inside, and they couldn't crowd the entire inside space with columns. They want to have the liberty of had that full 1 square width of our module. They had to span that space not with stone, with more tensile capable material, the wooden rafters. And so typically today when you see the ruins of a temple, the stone is left and the rafters are long gone because it's much more temporal type of material.
Because the columns are large, there was not much space inside the rooms. They wanted one square width in the model, but they couldn't do it with the stone because the stone doesn't expand. So instead, inside the buildings, they used wooden rafters to support the height and the weight. The rafters were both horizontal and vertical. That's why in the ancient Egyptian temples, the wood rafters are long gone, but the stone remains.